Hello everyone and welcome to the final video of the Conservation of Energy and Momentum unit. Our essential question is, how can conservation of momentum help us explain and predict the motion of colliding and exploding objects? Let's look at how momentum is conserved in closed systems and what that means. It means a couple of the following things. The first thing it means is that the total momentum in a closed system is always constant or doesn't change. So if all of it adds up to 1, it will always add up to 1 if it's conserved correctly. And that holds up throughout time. So if yesterday the total momentum was 1, 100 years from now the total momentum of the system will be 1. Even if individual momentums change within the system, the total momentum will still add up to 1. So what are some implications of these rules? This means that the results of collisions and explosions can have expected outcomes. When an object collides or explodes, their velocity will change. You can increase your velocity in magnitude, or you can decrease it. You could also change directions, going from positive to negative or vice versa, or you could do any combination of those things. And since momentum is equal to mass times velocity, if you change velocity, your momentum will change. The law of conservation of momentum means that for every object that gains momentum, another object must lose an equal amount of momentum. So if object A gains a momentum of 10, object B will lose a momentum of 10, so that the system of object AB has a constant momentum. So now we're going to use our conservation of momentum principles to predict the outcome of this little explosion right here. We've got two figure skaters that are going to shove each other. They have equal mass, and what you might predict to happen is that they will slide off, and both of them are going to gain some velocity. And this is true, but what you might not know is that one of those velocities is going to be negative, and one of them is going to be positive because they're in opposite directions. And we can look at the values for velocity and mass and show how this doesn't violate the laws of conservation. So let's draw our before and after systems so we can show how momentum is conserved from one moment in time to another. Their mass will be conserved because hopefully one of the figure skaters did not get horribly disfigured or double in size in this brief moment. So let's look at how their velocity and therefore their momentum is conserved. At the beginning in time, both of them have a 0 momentum, and then if we add those two momentums together, we get 0. If we go ahead in time to after the push, because we want to conserve momentum, we're going to write total momentum underneath as 0 as well. And then we're going to look at their velocities to see how this works. One of them has a positive momentum because they have a positive velocity, and the other has an equal and opposite negative momentum. And if you add those two together, you're going to have 0 momentum. So momentum is conserved. We did a great job, and we can rest well at night. But what's going to happen if our two objects do not have the same mass? So here we have this big Michigan football player and this tiny gal on ice skates, and they're going to push off of each other. So go ahead and make a quick prediction. Okay, let's see what happens. The football player, because of their large mass, is going to have a small change in velocity, and the small elementary schoolgirl has a small mass, so they're going to have a large change in velocity. But how does this fit our laws of conservation? Well, let's draw our before and after system. And even though they're going to have very different velocities, because velocities are not conserved, they will have equal but opposite momenta. So here we have a big mass and 0 velocity is no momentum for the football player in the before system. And we also have the elementary school world with a small mass and a zero velocity. So our total momentum is going to be zero. And since we want to conserve it, let's bring that total momentum into the future, and let's look at how our new momentum look for each individual. So we need to create our negative momentum. So we're going to have not negative mass, but negative mass times velocity, and that just means our velocity number is negative. And we're going to add our small mass and big velocity together, and those numbers equal and opposite will come out to zero, and it works just like our figure skater problem earlier. So momentum conserved, velocity not conserved. That's the big takeaway from this. So we're going to look at a tool called the MVP chart, which is kind of like a Sudoku puzzle for solving these before and after momentum tracking problems. So set up your two systems, before and after, and the system we're going to look at is an event that happened, or probably happened in Earth's past, when a planet-sized meteor, or maybe it is a planet, collided with the Earth back in the past. It was Mars-sized, and it was named Orpheus. So let's look at what we can do to conserve the momentum and try to learn a little bit about those systems as they collide. We're going to make two charts. We're going to make our chart on the before side, and we're going to make our chart on the after side, and you're going to have variables for mass of Mars, mass of Earth, velocity of Mars, velocity of Earth, and momentum of Mars and Earth. And on the after system, the Mars-Earth collision combo, it's going to have a mass, and the momentum is going to have a variable as well, and so our velocity also will have a value. And there are some rules to this. Our first rule is that our mass is going to be conserved, so Mars plus Earth is going to equal Mars, Earth. And our momentums are also going to be conserved, so the total momentum for this side, P total, is going to be equal to our total momentum over here. But velocity is not conserved. We cannot just add together the velocities of Mars and Earth at the beginning and expect them to be the Mars-Earth velocity at the end. And there's some reasons for that. The rest of it you can kind of solve like a Sudoku puzzle, right? If you know one value and you know whether it's conserved or not, it will lead you to the equation to figure out the other values for either adding, subtracting, or dividing. Okay, so let's look at why velocity is not conserved. So why isn't velocity conserved? Objects change velocity during collisions or explosions, and smaller objects have to change velocity more than bigger objects for the same amount of momentum because of that linear relationship between those things. So imagine a bug, and it's flying 60 meters per second in the negative direction at a bus that's going 60 meters per second in the positive direction. The bus and the bug will not change velocity by the same amount. A bug hitting a bus will not cause it to stop. The bus's velocity will barely change because of its relative mass. It might go to minus 59 meters per second, but that's only if it's either a very small bus and a very large bug. But the velocity change for the bug will be dramatic, even though their changes in momentum will be the same. So it's important to remember that mass has an inverse relationship with change in velocity in a collision or explosion, or a fixed momentum. So, to summarize, how can conservation of momentum help us explain and predict the motion of colliding objects? Go ahead and fill out your summaries at the end of your notes and do your extension questions. Thank you.